Okay. How many people do I have? So, two. That's the number. Okay, so we'll just do with the two that we have. Now three. Thank you for coming, guys. Thank you. So, I will solve some problems on the. Hello? Thank you for coming. Just want to mute myself on the. Okay, so this look, why don't we get this started? It's better we get started. So, for to begin with, let's consider the following function. To put this more, uh, so okay. Mm. Finally. Okay, so consider the function f of x, cosine of x plus 1 plus 1. Then I believe this was one of the questions we asked during the one of the midterm. Can the bisection can the bisection method be used to find the root of this function? Um, So as you can see, f of x remain a positive function because of cosine of x plus 1. So because cosine of x is between -1 and 1, cosine of x plus 1, it's between, uh, so that will be between -1 and then 2. So f of x is a positive function. So we cannot, and because of that, and therefore, positive for all x that is within the domain of f. So therefore, we cannot apply bisection method. That's to kick off our section. Cannot apply bisection method. Okay. So let's continue with a more robust type of problem. Maybe we'll do the error, or then we'll come back to quadrature, finish with Newton methodology, main b, and then we'll pass by, so, step by step. Let's go to the error, the integrals, okay? So let's consider the following integral, the defined integral. Consider the integral from 0 to 1 of sine of 2 pi x, we divide by epsilon dx, where epsilon is some positive constants. Okay, so the first question is this. If you have a question, do not hesitate to stop me, right? So if we take h, that is 1 divided by n trapezoidal, so n trap, for a positive, for n trap, that is a positive integer, okay? So belonging to what I call n star. N star is the set of a positive integer. The question is this. We wanted to write down, so I know what I'll do. So the question is this. Let's um, write down the composite, the CTR. So the composite trapezoidal rule apply the integral. Okay. So you remember the rule, right? So if the h is given, then the CTR, right? So you have to, it's not the CSR, but it's the CTR. So CTR will imply that the quadrature will be of the form CTR with h, that will be h divided by 2, the h with the n trap, f at x0, f of x is sine of 2 pi x divided by epsilon, so which is added to the sum j, that is 0 to n trap, like this, minus 1, subtract -1 because we will write the n term later, f at xj plus f at xn, the last term, like this. Okay, so because of the function f, then this become h divided by 2. You take that as the sum first of j that goes from 0 to n trap minus 1, n trapezoidal minus 1. The f of xj is the sine of 2 pi x at j, divided by the epsilon, okay? But since it is xj, so we need, let me write it so that it make more sense. So like this, so that will be 2 pi. So with the xj first, divided by actually the epsilon, okay, it's the sine of xj, right, like this, plus plus actually sine of 0, the sine at 0, like this, which we know that it is 0, and the x0 is 0, and then the xn trap, the latest term, the integral goes from 0 to 1, so the latest term will be 1. So plus actually the sine of so the sine of 2 pi, the 2 pi epsilon with the last x, which is 1, the 1 over here, and then we can close the big bracket. So this is h divided by 2, the sum, j that goes from 0 to n trap, but n trap minus 1, sine of 2 pi, so the 2 pi with j, dxj divided by well, n trap, which time epsilon plus the sine of 0 is 0, that will be the sine of 2 pi divided by epsilon. So the reason here is the reason of the h multiply the number of term for the xj. If you take xj, the xj in the distribution, that will be x0 plus, well, actually j which multiply h. But the x0 is 0, so the xj is just j which multiply h. And the j which multiply h is, that will be the j 1 divided by n trap, like this. And that will be this. And that's what you are over here. Okay. All right. So this will give us, we'll close the bracket over here. So it will give us, well, it give us, yeah, you cannot do more change. The sum, let's see if we can. 0 up to, we have n trap, but minus 1 with the sine of 2 pi j divided by n trap, but with the epsilon like this. So plus the sine of 2 pi divided by epsilon. There is nothing else that we could add. Any question? Any question? So that this will be the trapezoidal rule for the given integral. Okay. If you have a question, throw them in the chat if you want. You cannot speak. All right.
I
So
have a question.
yes, go ahead.
Um, oh, on the last step, is it n trap times epsilon?
Yeah, you mean this one? Yes, this one. This one, right?
Yeah,
Yes,
times
n
epsilon.
trap epsilon.
Okay, thank you.
Mhm. Okay, so let continue. Okay, so there's a big question. Estimate the number of points and the number of points necessary to achieve. So to achieve an error, so an error smaller than some positive number, error smaller than some positive number tau, like this. And then your answer should be in terms of epsilon and tau. All right, so we know that the trapezoidal, the CTR, so the CTR, we know what type of error it has. The trapezoidal it has an error, big OH square, but precisely, uh, you know, EH, E of H, so which is minus divided by 12, H square, F second of some xi, we call it mu in our case in the class. So some mu, the mu is between A and B, okay, with that is between A and B. And yeah, that's what it says. But the B here, our A, remember the A is 0 and the B is 1. So B minus A is then 1. So you can arrange the EH into given the information. So that will be negative 1 divided by 12 H square with F second of mu. So it's like that. Okay. Okay. So there is one additional thing that we know. So we know that our function f of x is sine of 2 pi divided by epsilon x. Then if we take the derivative, the second derivative, because that's what you're interested, the first derivative of form of x is 2 pi epsilon cosine of the same thing here. And the second derivative f second of x, so that will be 2 pi divided by epsilon raised to the square minus the sine of 2 pi epsilon x, like this. So we can we can bound the f second of mu for all of the mu that are between 0 and 1. So it will be bounded by 2 pi divided by epsilon raised to the square for any x or mu that is between 0 and then 1, like this. Okay, so if we want the EH to be smaller than tau, so if we want, if the EH, we want it to be strictly smaller than tau, like this, then we need the term in the absolute value, then the error term that we have in the absolute value, the h squared divided by 12 with, well, the upper bound for tau, which is 2 pi divided by epsilon raised to square. So it has to be smaller than the tau. Okay. So, but since I have h, that is the h, it's b minus a divided by n. That'll be 1 divided by n trapezoidal. I'll change it over here. So this become, so we can say that I have 1 divided by n trapezoidal. Okay, raise the square here. Then I have divided by 12, 2 pi epsilon square smaller than tau, and like that. So overall, I can, I want the answer. We said that the answer must be as a function of only epsilon and tau. It's the trapezoidal that we're interested in. So the n-trap that we're interested in. So I'm going to put the n-trap on the right side of the inequality. This is 1 divided by tau, 1 divided by 12, 2 pi epsilon raised to the square, which is smaller than n-trap raised to the square. So, but this is it. Okay. And that gives us the answer that is required. And if we want, we can, we can just take the absolute, the roots of both sides to have the n-trap itself. So that if we take the root of what I had previously, its root is 1 over tau, like this, 1 divided by 12, like that, 2 pi like that. So it is smaller than root of n-trap square, which is, so this will be 1 root of tau, 1 root of 12, 2 pi over epsilon smaller than n-trap. Is it clear? Is it clear? Are there questions?
Could you go back to the part where you said like what f prime of x was and f double prime?
This
I
one.
think it was one more page to the left.
One more.
Yeah, that one. Okay, thanks.
Let me know when you're done. While she's taking notes, give me a second. Okay, shall we continue? Shall we continue?
Yeah, thanks.
Okay. All right. So next question. In the next question, C, suppose that there exists a quadrature method, let's call it QM. Okay, whose error satisfy? So satisfies E error, which is 1, the root of NQM, regardless of the integrand. Okay, all right. And where NQM is the number of points that you use within the quadrature. And the question is to estimate the number of points necessary necessary to achieve an error which is smaller than some positive number tau. Achieve an error that is smaller than some positive number. Some positive number tau. Okay. So the error is already given as equal that. So we want to see so you want to see actually you want to see what is approximately the value of n indexed by q such that such error the error we said is some 1 divided by root of nqm, but it is smaller, so such error which depend on the qm is smaller than some tau. So this gives us that 1 divided by tau which is smaller than root of NQM. We will take the square smaller than, it's strictly here, smaller than N if QM, like that. Okay, that will be the relationship. Is it clear, guys? Is it clear? Let me know if there are questions. D. So in the D, assume that tau is 10 to the power negative 4. Using the answer in the previous part. On the previous parts, explicitly determine explicitly determine NQM. NQM in this case. Okay, so we'll do that. Okay, so maybe I'll take all the questions and we can address them on one-on-one basis. Using this and the answer from the second question. And so your answer from the second question. Okay, so from the second question. So we respond to the question at what value epsilon does it become more computational? Does it computationally efficient? And to use QM, so the quadratic method, instead of trapezoidal composite rule. Okay. All right. So why don't we do that? So because look, the question is this: if we suppose that tau is 10 to the power negative 4, we want to use the answer from the previous part. Let me remind you, the previous part state that 1 over tau square is smaller than the number of grid points required in the quadratic methodology. So if the tau is 10 to the power negative 5, then this will entail that our NQM, the NQM will be greater than 10 to the power 8. It's actually 10 to the power negative 4 square. So that, and then you pass that on the other side, it will become greater than 10 to the power negative 8, which is required to do this quadrature methodology. I mean, that's a hell of quadrature to perform So QM then. Okay. All right. Now, the second question asks to use the answer for part B. So the answer from part B is the CTR, and the error was NTRAP, which was greater than. Okay, we have NTRAP was greater than the NTRAP for part B. The NTRAP, let's go back there and see. It's the CTR, yeah, this one. The NTRAP was greater than 1 divided by root r for tau, and divided by root r for 12, 2 pi divided by epsilon. Okay, so 1 divided by root of tau, root of 12, 2 pi epsilon was greater than NTRAP. It was smaller or greater? It was smaller than NTRAP. Well, let me make sure that I'm writing there. Yes, it's smaller than NTRAP. Okay, so like this. So from there, we can say that the NTRAP is greater than 1 divided by root of tau, 10 to the power negative 2 then. Okay, 1 over root of 12. Root of 12 is approximately 3 point, maybe 5 or 6. 3.5, let's say. 2 pi. So the 2 pi divided by epsilon, or it's one of the things that we can do over here. So we can say that it's 1, 2, root of 3, 2 pi divided by epsilon. Okay, like this, and we can simplify the 2. All right, so we can simplify the 2. And well, if we do that, so then it's become 10 to the power NTRAP here is greater than, well, 2 to the base, so that will be greater than 2 to the power positive n. So divided by, we can simplify the 2 by the pi over here, and then I have epsilon. So I have pi divided by root of 3, which multiply epsilon, 1 divided by epsilon. Like that. Okay. But now we want to estimate such that the error, I mean, the question is at what value of epsilon does it become more computational efficient to use the QM? So it becomes computational efficient to use the QM if the error generated by NTRAP is greater than the error generated by QM, right? So CTR is less efficient QM if actually the error generated. So I have here 10 to the power 2, which multiply. So you have pi divided by root of 3, 1 over epsilon, was greater than the error 10 to the power negative 8. And then from there, you can deduce what is the epsilon. So this implies that this is 100 pi divided by root of 3, like this, 10 to the power 8 that is greater than epsilon. So meaning epsilon is smaller than 100 pi divided by 10 to the 8th root of 3. So like that. And we can, of course, we can simplify. This is 10 to the power, but my epsilon, if you want, is smaller than 10 to the power negative 6 pi root of 3. And that will be the last answer that I have.
Professor, isn't this comparing the NTRAP and the NQM rather than the errors?
I didn't hear you very well. Can you speak louder?
Yeah. For this part, is it comparing the errors or the NTRAP and the NQM?
Yes, yes. What I'm saying is, if you want to choose one methodology above the other one, then the one that you choose has to be error efficient than the one you leave off. Okay. So for that to be error efficient, you need each error to be smaller than the error generated by the other methodology. That's what I apply here.
Okay, thank you.
Yeah. Okay, so let continue. Um, in the next assignment, we are going to consider x0, that is a real number. And then x1, that is x0 plus h. And then x2, which is x0 plus wh, like this, for some h, which is positive. So find the ABC, find the parameter ABC, okay? So that A f at x0 plus B f at x1 plus C f at x2, that is f prime at x0 plus big O of h squared. Okay, so we wanted to determine three constants, A, B, and C, for which this relationship is true. Let's use Taylor theorem. We can claim that f at x0 plus h is f at x0 plus h f prime at x0 plus h squared divided by 2 f second at x0, but plus we stop at the other h cube over factorial and 3 f second, f third over epsilon 1, like this. Okay. Then for some reason, I'm going to write the same thing, but f at x0 plus wh. Well, I mean, for some reason, the reason are here, right? You have f at x0 at x1 and at x2. So that will be f at x0 plus the wh f prime at x0 plus look at wh squared, which is 4h squared divided by 2. So that will be wh squared f second at x0 plus, well, so you have to divide this time by factorial 3. So this will give you h cubed. Of course, there is 2h to the cube, which is h, you simplify by 2 here, give you 3. Then multiply f1 to 3, f third of c2, like that. Okay. And then you look at the possible combination that you can have to have f prime at x0. It's like an approximation that we are doing. So if you do that, we want to simplify this term. If we want to simplify them and maintain f prime at x, then the idea will be, well, you take f at x0 plus h, and then, well, if you do that, say you subtract, I don't know, it's, yeah. Let's say we did the 4 times that, yeah. Okay, yeah. Okay, so then let's examine f at x0 plus 2h minus 4 f at x0 plus h. Okay, so when you do that, you'll find this one minus 4 times that. So it will give you 3 or negative 3 f at x0, f at x0. All right. Then you will do the derivative term. So the derivative term will be minus 2h like this, f prime at x0, the first derivative term. And then the remaining term, so for the remaining term, let me see. So that will be 2h minus, actually, yeah, h4 divided by 3h cubed, yes. And then another 4 by divided by 6h cubed. Okay, so we put that together, and that will be plus 4 divided by 3. So 4 divided by 3, h cubed. H cubed f third of C1, like that, minus 4 divided by 6, h cubed, f1, 2, 3, C2. Close it like that, okay? So with that said, if you take, you can pass the f at x0 on the other side of the equation. So let me see, that would be f at x0 plus 2h minus 4 times f at x0
Could you
plus
lower the
h.
please?
Then we pass negative 3f at x0 on the other side here. So we will have f at x0 plus h, or actually plus 2h, minus 4 f at x0 plus h plus 3 f at x0. So minus 2h f prime at x0. And then you add it to that, well, 4 thirds f thirds C1. And when you simplify, 4 divided by 6 is 2 thirds f thirds of C2, close the bracket. And well, then well, you can just pass the h on the other side, because the h divide everything that you have. So you have 1 divided by h, f at x0 plus 2h minus 4 x0 plus h plus 3 f at x0, so which is, so this will give us, if we take, so let's say we take divided by 2, that'll be better. So this will have give us negative f prime at, so it's negative f prime at x0 plus 2 thirds f 1, 2, 3 C1 minus 1 third f third at C2, so like that. Okay, so better this one, there is h that I forget here. H to the cube multiply all that expression. So h cube multiply. So this will be h squared. Okay. All right. So if we do that, then we can even, apply the negative sign that is here. Can apply the negative sign that is here. So this will be 1 divided by 2h with, well, actually, minus f at x0 plus 2h plus 4 f at x0 plus h minus 3 at f at x0, like this, is f prime at x0 plus big O of h raised to the square. So the value of a, so this implies that the value of a is minus, so that will be minus what? Minus, it said that, yes, so okay, so the a applied to that. Yeah, that will be minus 3 divided by 2h the B value, when you look into that, the value of B is this 4 divided by 2h, so that would be 2 divided by h then. And the value of C, so the value of C, see what the value of C is. Minus, yeah, with this one, negative 1 divided by 2h, divided by 2h. And that will be it. That one is simple. Any question? Any question? Okay.
On the like part, the right hand side of the equation, when you say like 2/3 f triple prime of what? Is that x1? Or what's like inside the parentheses?
On this side or another one?
Yeah, on that part.
So which line?
The part that says plus h squared times
So
2/3 f triple
which one?
prime.
Which number line? 1, 2, 3, so I can follow.
3.
Here. Yes, what is the
Yeah,
question?
right under that, right under that. Yeah. What's inside the parentheses?
No,
I can't
because I
read it
have
exactly.
the HQ was here. I have a H here. Then I divide by 2H, right? So when you divide all this with negative 2H actually, but by 2H first. So when you divide by 2H, the 2H goes here, and there is H cube that is here, right? So the H cube will become then H square. Then I'll drop the 2 here with the 2 that is here. That's what I did.
Okay. And then when it says f triple prime, what's right next to that? I just can't read that very well.
Double prime. You mean here is triple, epsilon 1, Xc1.
Oh, epsilon 1.
No, Xc. It's
Okay, thank
this
you.
one here, the one that is here that I reported here. And
Okay,
the
thanks.
second one is this one. Is it clear?
Yeah.
Then I have a question on the Newton method, but I think now you're familiar with that, so I'm not going to do that, right? But maybe let's see if you write that down. It might inspire you a little bit. Let that the function f is C infinite over A and B. And let P belong to the set AB. And suppose that give me a second. So let's assume that the function f and its derivative are indefinitely differentiable. And suppose that f at p equals 0 and f prime at p is not 0. So why don't we show that the g of x is x like this as a fixed point. So it has a fixed point at x equal p. So that one is easy, right? So the fixed point, you take a g at p, and then the g at p is p minus actually f at p over f prime at p. But so f at p equals 0 because, uh, so f prime at p is, the assignment say that, okay, so you have f at p equals 0. The f at p equals 0 is given. So this is just p, and p is a fixed point for the function g. Okay, easy because f at p is 0. Second, guys, because what there is no because the assumption said so. So p is a fixed point. Then the next question is this: b. Um, if we write p or p naught b within the set AB and define a sequence. A sequence P0, P1, P2, Pn by the fixed point iteration. Okay, so that's a fixed point iteration given by Pn plus 1. That is d at Pn, like this for n greater than 0. Okay, all right. If we assume that Pn, uh, converge toward P as n go to infinity, like this. So prove that the sequence converge with at least, prove that with at least um, order alpha that equal to, okay. So look, if you're under the assumption that the fixed point iteration converge, so the order of convergence is connected to the number of vanishing derivative of the function g, okay? And that function is the one that is involved in the FPI methodology. Okay, so we said we wanted only to show that the convergence is the smallest one is greater than or equal to. So the smallest one being 2. So it's just enough to prove that G prime at P equal 0. Okay, so we only plus the argument that I developed earlier. So if you look at the G of x, is x minus f at x, f prime at x, but G prime at x is 1 minus f prime at x square and minus f at x a second of x. Then we divide with f prime at x raised to the square. Okay, so that's d prime at x. And that d prime at x, if you put f prime here, so this become, it simplified the f prime at x squared. It become f at x with f second at x, divide by f prime at x raised to the square. So with this d prime of p, because of f of p, the d prime of p equals 0. But f prime at p is not 0. It's not 0. And then it will give this, giving the quadratic but order of convergence. Okay. All right, guys, I think I'm going to stop here for today. And I'll open my Zoom accounts in the evening from 8 to 9 on Monday. So I have my other class. But if you have a quick question you want to, you want to look into, let me know so I can address them on that day. Thank you very much for coming, and I just look forward to see you, um, you during the test, or Monday or during the test. Thank you, guys.
Thanks.